Okay, so welcome to this new lecture. So what we will do is that we will just review the previous lecture, and before we start the new lecture. So this is where we started the last lecture. In this lecture we discussed the case of diffusion in a lightly doped NaCl. This was done to differentiate between intrinsic diffusion and extrinsic diffusion. And this is because that as you know that sodium chloride is a material which predominantly has Schottky defects in the pure state, which means it has sodium and chlorine vacancies, and sodium vacancies being more mobile are the defects which diffuse. At the same time, sodium chloride in most practical applications tends to contain some impurities like cadmium chloride, and these impurities give rise to again sodium vacancies. So there is a competition between the sodium vacancies which are created thermally as by means of Schottky defect formation, and there are some sodium vacancies which are created by impurity concentration. So impurity concentration determines that whether you will have sodium vacancies created by the impurity or by thermal means. And as you know that in impurity concentration is independent of temperature. So the vacancy concentration which is governed by impurity concentration is temperature independent thing. So as a result, what we have here is we have a region in which the vacancy concentration is constant, which is determined by the impurity concentration, and when the thermally generated vacancies start increasing in number, then those vacancies dominate. So as a result, you have two regions. You have extrinsic region which is dominated by vacancy created by the impurities, and then you have intrinsic region which is due to vacancies created by thermal Schottky defect formation or thermal means. And as a result, this is also reflected in diffusivity. So you have two regions of diffusivity. In the extrinsic region, since the vacancy concentration vacancies are already generated by impurities and their concentration is much more larger as compared to intrinsic or thermally created vacancies. So the only energy barrier that needs to be overcome is the migration energy. So in the extrinsic region, slope of log d versus 1 by t curve will give you the migration energy. On the other hand, if you look at the plot on the left side, so there is a crossover from extrinsic to intrinsic, and at the crossover the concentration of vacancies due to thermal and impurity means are equal. And in the left hand side region, which is also called as intrinsic region, now you need to spend two energies. First energy is the energy which needs to be spent in creating the vacancies, and then second energy is the energy which needs to be spent in moving these vacancies. So as a result, the activation energy goes up. So this has to be taken into consideration, and as we will see subsequently, this has its manifestation in the conductivity as well. So and then we looked at then we moved on to talking about the properties such as mobility, which we will soon relate to electrical mobility, and mobility is defined as nothing but velocity per unit of force. And so there could be various different kinds of mobilities. In our context, we took the hypothesis of Einstein, who said that when you have diffusion in a system as a result of chemical potential gradient, there is a force which is exerted on the species, and this force gives rise to a mobility called as absolute mobility. And from this we can work out what is the flux, and then we can relate this flux in terms of chemical potential gradient, which can then be converted into concentration gradient, and what we get is a relation between the diffusivity, which is given from Fick's first law, which is J is equal to minus dC by dx, and this comparison between the expression which is worked out using this mobility model or Einstein's model is compared with the Fick's first law, and then you get the value of diffusivity as di or diffusivity of a species I is equal to RT. R is the gas constant, T is the temperature, and Na is the absolute number, RT by Na into Bi, where Bi is the mobility or absolute mobility of species I, or alternatively it is equal to KT by Bi, and this is called as Nernst-Einstein relation. It is a very important relation because it has its own importance in the ionic conduction, actually in any kind of conduction, because you can do the same exercise for electronic conduction as well. Now, in the context of electrical properties, we can calculate what electrical force is. Now, electrical force is nothing but, as you know, in an electronic system like metals, F is equal to E. Now, in this ionic system, it becomes F is equal to ZIE into d phi by dx, which is nothing but E. And then we know what flux is. Flux is nothing but Ci Vi. So, now what we do is that we substitute for Bi and Fi in this expression. So, we get the Ji expression in terms of Ci, Ti's and E, and we equate it to the original expression Ci Vi. So, what we get from here is an expression for Vi, which is Zi by Zi di Zie into capital E, which is the field, divided by kT. And from this, what we get is the mobility. This is called as ionic mobility. This is not electronic mobility, this is ionic electrical mobility. Okay. So, this is mu I is equal to Zie di by kT, because we know that in case of electrons, mu I does not depend upon diffusivity, as we will, as I will just come to that in a minute. And here, so you have this dependence on temperature and diffusivity. So, this is your mu I for ionic systems in case of ionic defects. In case of, so we just went on to compare this ionic conduction with conduction in metals, and in case of metals, we saw that the mu which is called as electronic mobility is again you can relate it to V divided by Ze, or V basically velocity by force, or Ee in this case. So, this becomes E tau by m. Okay. And this E tau by m is nothing but your electronic mobility, and where tau is the relaxation time, which is the average time spent between two successive collisions. And as you can see now, whatever factors increase tau, they also result in increase in mobility. So, typically tau decreases as temperature increases, because electron phonon scattering increases, because atoms vibrate more and more as you increase the temperature, as you know, and as a result electrons scatter more, and this relationship goes as T to the power minus 3 by 2, and this tau also decreases as the impurity concentration increases. But there is, as you can see, there is no relation like dependence on D explicitly. So, there is no diffusivity relation dependence, there is a temperature dependence which is implicit, you can't see it here, but tau depends upon T. So, as a result, this is the difference between electronic and ionic. And another difference between metals and ionic solids is, in metals and semiconductor, the transport takes place in the bands. So, it is a band transport. So, whether it is a metal or semiconductor, although the relationship of conductivity with temperature is different, because in semiconductors what happens is, as you increase the temperature, the carrier concentration goes up. However, the mechanism of transport is similar in both these materials. It is called as band transport. Within band transport, electron moves between the energy levels. Now, in case of ionic solids, the transport is called as polaronic transport, and this happens by hopping. And hopping is basically, so I will come to now polaronic transport in much more detail in contrast to metals. So, we will start this new lecture by discussion on ionic conduction. So, we are saying that this is polaronic transport. Now, what happens in these solids is, in ionic solids is, electrons is in close proximity of the lattice. It is not free, unlike in metals. So, what happens is that the moment it is in, since the fact that it is in close proximity of the lattice, it tends to polarize the lattice. Now, how? So, suppose you have a lattice like this. Okay. So, suppose this is your one type of ion, and this is your another type of ion. So, let us say this is your let us say K plus, and this is let us say your Cl minus. Okay. Now, suppose you have electron somewhere here. Now, when you have electron which is localized to the lattice, what happens is, this electron, it pulls these ions towards it, and it pushes these ions which are the positively charged away from it. So, what happens in the end is you have a distortion. So, if you just zoom this area and look at it now, so what it becomes is you have electron here. So, these two positive guys, negative guys, sorry, they come close to this electron. So, they are pushed towards as a result of Coulombic attraction and as a result of Coulombic repulsion. I should make them smaller, they are cations actually. So, these, excuse me, let me just redraw this picture, taking the size little bigger. So, this is the electron. I am saying that these K plus ions, which are the shaded ions, go away. So, what you have is K plus ions, they go away. So, suppose this was the equilibrium position, so both of them are moved out. On the other hand, the chlorine ions, they have come closer. So, they have moved this way. So, what you have is a distortion. So, this distortion results in a region which is called as a, so this distortion, this association of electron or carrier with the lattice results in a polarization. As you know, polarization is nothing but shifting of charges, charge centers away from each other. So, for example, this center which was here earlier, now it has moved to this direction, and this center which is here now, it was somewhere here. Okay. So, it has moved to this direction. So, this has resulted in polarization of the lattice as it is called in scientific language, and this whole entity is called as polaron. So, now naturally more the polarization of the lattice, which means more closely the electron is associated with the lattice. So, as a result, size of the polaron determines how closely, how loosely bound the electron is with the lattice. So, smaller the polaron is, which means more is the interaction of electron with the lattice, and larger the polaron field is. If polaron field is larger than this small group of atoms, then it is called as a weakly interacting or weakly connected weak polaron. Now, this polarization also results in changed effective mass of electron, and which is called as effective mass. So, it is given as m star. So, typically it is larger than mass of free electron. So, basically it has electrons in the form of polaron, carriers in the form of polaron have become heavier as compared to free electrons. So, naturally one of the repercussions of this is going to be that it is going to be difficult to move this electron now. So, it does not move, and moreover, since this electron is now associated with the lattice, it does not move freely, it does not move freely in the band. So, rather if it has to move, how it moves is, so now suppose this is one site, this is another site, this is another site, this is another site, and suppose the electron was associated with this site. So, what happens is it goes from this state to that state by hopping, and from this to that by hopping. So, basically it hops between different atomic states, and this is called as polaronic conduction, and this is what is ionic conduction basically. So, now as you can see, since this is a hopping related phenomena, so hopping of carrier, and this hopping tends to be temperature dependent, just like diffusion. So, as a result, in these systems the mobility which you see is dependent upon temperature in the form of exponential minus some energy q divided by kT, and so this mu I would be of this form in ionic systems as a result of this thermally activated hopping phenomena. Okay. So, for now this can be interpreted in various different ways. For example, you take the example of an oxide BO, and this is doped by, let us say, A2O, and the example in our case could be doping of NiO nickel oxide by Li2O. Now, when you dope nickel oxide by Li2O, what are you going to get? Li2O will result in Li at Ni site. So, when Li goes to Ni site, it is going to have one negative charge on it, and let us say you have oxygen going to oxygen site, and if you have now, in order to maintain the site transport, if you have both the Li's going to oxygen site, then you are going to find oxygen vacancy, or let us say you bring in the oxygen from outside. So, both the oxygens are occupied. In this case, what it can result in, either the formation of a hole, right, or you can represent this by Ni at Ni site. So, this is nothing but oxidation of nickel. So, what it means is that formation of Ni3 plus. So, what now you have is lattice sites will be like this. So, some of this will be Ni, most of these will be Ni2 plus, and some of these will be Ni3 plus. So, what happens is this extra electron or extra charge associated, in this case not electron but hole. So, in this case this extra charge associated with this Ni3 plus site can be, so what happens is the electron will, carrier will move like this, or in this case rather it will move like this. So, or if the electron moves, you can imagine in whatever way, hole moving to this side or electron moving to this side, the result is when you have this movement taking place. So, each of these Ni3 plus will be converted into Ni2 plus, and Ni2 plus will be converted into Ni3 plus. So, this will be subsequent movement from one side to another, and this is why it is a hopping related hopping kind of transport. Now, what happens when you dope it? So, conductivity, you can say resistivity versus percentage lithium. So, as you can see, as you introduce more and more lithium into it, you are going to introduce more and more holes or more and more oxidation of nickel. So, what happens is, as a result you have the conductivity of this material, it goes down, straight line, not a curved line. Okay. So, this conductivity resistivity goes down. The resistivity you can write in ohm centimeter, okay, and this is because of this increase in the carriers which can move between the nickel sites. So, this is one example. You can have many examples. You can have formation of vacancies. So, if you have, for example, formation of vacancies, then so you have this OO sites, and then you have this vacant VO site. So, you will have now charge transport between these two sites, all these two sites. So, charge will again move in this row of oxygen atoms, giving rise to hopping kind of conduction. So, this is another. So, this is basically this kind of transport is thermally activated phenomena, which depends very strongly upon temperature. And so, as a result, mobility is exponentially dependent upon temperature, having an activation energy, let us say Q, and conduction in such cases is also determined by things like what is the concentration of impurities, especially those impurities which introduce extra defects or extra carriers into the system, of course within the appropriate limits. So, typically you will find as you introduce impurities which give rise to defects, the conductivity tends to go up. On the other hand, if you look at metals and semiconductors, well, I mean you can increase the conductivity by doping, but if you look at the pure semiconductor, for example, in the metals and semiconductor where band transport is the mechanism of transport, the mobility is affected by only temperature. Okay. So, so this is what it is. So, basically to summarize this part, in metals and semiconductors, mu decreases as temperature increases. So, this is mu electronic or mu hole. Okay. In ionic solids and this is typically T to the power minus 3 to 3 by 2 relation. In case of ionic solids, mu I in this case, mu I increases as temperature increases, and this is because of this relation of exponential minus q by kT. So, this basically you can imagine as if you have counter movement of vacancies, because a charge is associated with the vacancy. So, you can in the previous case you can say it is the movement of Ni3 plus ions. In this case it would be a movement of vacancies. So, instead of charge transport you must consider this rather as a ionic transport. So, that is why conductivity in ionic systems is a hopping kind of system, because here the defects move, and movement of defects is nothing but diffusion. So, the typical values for conductivity mobilities in so the strongly interacting systems, system where the polarons are smaller size, mu's are of the order of 0.1 centimeter square per volt second, and these are about, and in case of weakly interacting systems, where polaron interaction is weaker, the mu's can be of the order of 100 to 1000 centimeter square per volt seconds. So, I will give you some values of mobilities which you can just have a look and see, analyze them yourself. So, for example, I will start with some of the ionic non-ionic systems as well. So, so mu here is in the units centimeter square per volt second. So, for example, for diamond, mu E and mu H, both electrons and holes. So, this is 1800 and this is 1200. So, diamond has actually very good mobility of electrons and holes, it is just that it has a very large band gap. So, as a result it is a very good insulator. Silicon on the other hand has about 1600 and 400. So, silicon has more mobile electrons as compared to holes. Germanium, which is also very good semiconductor, 3800, 1800. And so, these are your non-ionic covalently bonded solids. And if you look at compound semiconductor like gallium phosphide, it has much smaller numbers. So, these are approximate numbers, they are not absolute numbers, they are approximate numbers depend upon various factors. And so, now if you look at, for example, oxides like FeO, MnO or COO, these are typically metal deficient oxides. Metal deficient oxides means you will have holes. So, they are typically p type conducting oxides. So, these are all p type. This already we have learnt. So, here the conductivity mobilities are of the order of 0.1, very small, as you can see, it is a very small number, and these are typically very strongly interacting systems. And if you look at things like silver chloride again, silver chloride is a more electron transport system, and here mu E is about 50, units are always same in all the cases. In case of, for instance, tin oxide SnO2 is used as a conductor in variety of applications, especially in electronic applications as a electrode layer, conducting electrode layer. If you look at strontium titanate has about 6, and Fe2O3 has about 0.1, TiO2 has about 0.2. In the case of p type, again Fe3O4 tends to be p type as well, this has 0.1, and so there are basically you have p type ionic solids, and so these are all p type ionic solids, because here whole mobility dominates over the electronic mobility, and these are your, so I can write p type, and these are your other ones are your electronic, predominantly electronic transport materials, and this is where your electronic mobility dominates. So, these are the values, as you can see, the values compare very poorly with the other systems. So, these mobilities are extremely low as compared to other materials, and since the moment, so we said strongly interacting systems and weakly interacting systems. Typically strongly interacting systems are ionic solids, and weakly interacting systems would be your semiconductors or even metals. Metals, there is no interaction at all, they are free electrons. So this is the picture which emerges when we look at the difference between the ionic and metallic conduction. So, again to summarize, the metallic conduction is basically you have free electrons in the metals, and those free electrons are free to move between the energy bands. So, the mobility there is purely electronic mobility, and that mobility is affected only by temperature. In case of semiconductor also, although the concentration changes as a function of temperature, again the transport is band transport, and again the mobility is dependent predominant only on temperature. In case of ionic solids, the situation is different. The concentration of carriers is dependent on both impurity concentration as well as temperature, but the mobility is a strong function of temperature, and it depends exponentially. So, and this mobility is more like diffusivity, because here the transport of charge is similar to transport of defects in the system, which is nothing but diffusion. So, that is why if you remember the previous expression in the previous lecture, here somewhere here. So, here now you appreciate this expression more. So, that mu I is equal to Z I E d I by k T. So, this mu I is a function of d I, and this d I is a very strongly temperature dependent. So, this is the difference between metals and again another thing is that ionic systems are polaronic transport, because here the electron is not electron is confined to the lattice sites. As a result, this confinement results in polarization of the lattice, and this whole entity is called as polaron. Okay. So, now what we will do is that we will look at the expression of the conductivity, what the conductivity is like. Okay. So, we know what the conductivity is. Conductivity is nothing but charge flux per unit area, flow of charge per unit area per unit electric field, and this has a unit of per ohm centimeter or Siemens per meter, and this conductivity is expressed as. So, what we are going to do now here is conductivity. So, conductivity is expressed as sigma I, which is nothing but conductivity of I species, let us say, and this is nothing but given as Q by T, which is charge per second divided by area. So, this is flux per unit area divided by your electric field E. Okay. So, this I can write as I by A into E, and I by A, as you know, is current density. So, this would be your flux multiplied by Z I E, and this would be divided by E, which is the electric field. Now, if you write the expression for J I, which is the flux, which is nothing but equal to C I V I. So, C I is the concentration, V I is the velocity, multiplied by Z I E divided by capital E, which is electric field. So, this J is nothing but flux. Okay. There is not current density, this flux. Okay. So, now again for the ionic systems we can use the Nernst-Einstein equation, and from this equation we saw that earlier mu I was equal to Z I E d I divided by k T. So, that is why the sigma I becomes equal to C I. So, you can change this a little bit. What you can do here is this becomes C I Z I E into mu I, because this V I by E will become mu I. This is velocity per unit electric force, which is the field. So, this becomes C I Z I E into mu I is Z I E d I divided by k T, okay, and this becomes equal to C I Z I square E square d I by k T. So, conductivity in ionic system, it depends upon concentration. Of course, concentration of carriers is important or defects is important, but it depends very strongly upon temperature, and temperature, because this d I is a very strong function of temperature. So, now when you plot this log d I versus 1 by T log sigma I, and this tends to vary like this, and this is nothing but your slope, which is nothing but minus q by r minus q by k. Okay. So, similar to now in case of if you have impure solids, similar to diffusivity, you will have two regions. So, intrinsic versus extrinsic. So, in case of systems having impurities, whether intentional or unintentional, it does not matter. So, you have when you plot log d log sigma versus 1 by T, you will again have, of course, if I plot both of them separately. So, this will be your intrinsic part and this will be your extrinsic part, and overall behavior would be like this. It is basically a straight line. My hand is not very stable. So, this is your extrinsic region, this is your intrinsic region. So, again the regions are similar as in case of diffusivity. The only difference is that instead of diffusivity you have conductivity. Okay. So, now what we will do is that we will now look at the, so this electron, now these ionic systems, they have of course ionic conductivity, as we have seen now. They also have electronic conductivity. The fact that they have a band gap and they have a certain number of electrons and holes in conduction and valence band as a result of intrinsic ionization. So, there will always be component of electrons and hole, intrinsic electron and hole concentration, which will give rise to your intrinsic conduction. So, just like in any other material. So, there will be, so the conductivity will be sum of this electronic conductivity, which is due to intrinsic electron and hole creation, and sum of your and your ionic conductivity, which is due to defect formation. So, the total conductivity now, so the total conductivity sigma total will be basically sigma ionic. So, whatever ionic species are present, and sigma electronic, okay, and this will be nothing but equal to sigma I, any kind of various species, and fraction of the conductivity carried by each of these species is called as a fraction of this conductivity of each species to with respect to the total conductivity is called as a number, which is called as a transference number. So, T I is equal to sum sigma I divided by sigma total, and this is called as your transference number. So, now you can see that if this is the case, then T1 plus T2 plus T3 plus Ti will be always equal to 1. Okay. So, this is your, so naturally when you have electronic conduction, then so in case of electronic conduction, T is almost equal to T electronic, and this will be equal to 1. And in case of ionic conduction, T will be equal to T ionic, and this would be equal to 1. So, and when you have mixed conduction, then of course T is a composition of both electrons and electronic and ionic conductivity. Okay. So, now what we will do is that I will give you some values of conductivity transference numbers for various ionic systems, and the thing to which note is that in case of metals and metals, the conductivities are very high. In case of ionic conductors, the conductivities vary within the range 10 to the -5 to at the most 100 Siemens per meter. And if you look at semiconductors and metals, these are orders of magnitude higher than what you see in metallic conductors, at least 3 to 5 orders of magnitude, and in fact it could be much higher. So, and the oxides are also of different types. The range is massive, because some oxides are easily reducible, some oxides are easily oxidizable, some oxides accept impurities much more readily as compared to other oxides. So, as a result, depending upon the characteristics in terms of defect concentration and carrier concentration, their conductivity is also vary significantly, and also it is dependent upon the diffusivity of species that are present in those systems. So, I will give you some of the values, and then we will move on to little bit more quantitative analysis of this ionic conductivity. So, in case of the T values, for example, I will give you, so what we have is compound name or formula, and this is, since it is dependent upon temperature, the temperature which I will, or range of temperature, and then T plus or T minus or T electron or hole. Okay. T plus or T minus is depending upon type of ion, positively charged or negatively charged, defect or ion. Okay. So, if you look at, for example, zirconium, oops, it's a little wrong, ZrO2 stabilized with 7% calcium oxide, and this gives you this is at a more than 700 degrees centigrade, and this gives you typically whole ionic conductivity of almost ionic conductor, and this T minus is because of oxygen ion conduction. Defects are oxygen vacancies, and since vacancies move, which means the oxygen ions also move, that is why it is noted as T minus. Okay. And this is very small, 10 to the -4, negligible. In case of beta aluminates, Na2O dot 11 Al2O3, these are called as beta aluminates or beta alumina. These operate at much lower temperature as compared to the previous one, and here sodium ions are the most mobile, and this is almost equal to 1, and these are almost nil, much smaller than 10 to the -6. Similarly, if you look at the case of iron oxide is at 800 degrees centigrade approximately, and this is again, now iron oxide happens to be a good electronic conductor. So, as a result, you have almost excellent electronic conductivity and very poor ionic conductivity of. So, here you have oxygen iron vacancies, and those iron vacancies mean you have movement of iron atoms. So, that is why you have T plus. Similarly, if you look at for example, Na2O, CaO, SiO2 glass, and here Na plus again, and it is almost equal to 1, and these are very small, and this is again much lower than 700 degrees centigrade. So, these are some of the typical values in these ionic systems. You can look at the books which I provided in the bibliography, especially the books of physical ceramics, that gives you some of these values, and also by Chiang, Burney and Kengeri, and then you have principles of electronic ceramics, Hench and West. these two books will be, so these two books will give you the some of the values of transference numbers in these systems. Okay. So, you have basically you have these in case of some of the examples of oxides. So, you have easily reducible oxides, and these easily reducible oxides are typically your titanium oxides or zinc oxide, which are typically, or let us say N type oxides. Okay. And SnO2, barium titanate, all these are prone to having N type behavior due to creation of either oxygen vacancies or which give rise to compensating electrons or something else, or you can have cation interstitial plus electrons. And the easily oxidizable materials are which are typically p type, and here we look at mainly materials like cobalt oxide, iron oxide, etc. These are all p type, and these are all metal deficient typically. So, these are some of the examples of these ionic conductors which are. So, we will take one example here. Just to see what it means. So, example we will take is conduction in magnesium oxide. Okay. Not that magnesium oxide is a very useful material from the conductivity point of view. We will just take this example just to illustrate our point. So, let us choose a temperature. So, we choose a temperature at 1600 degree centigrade, which is 1873 Kelvin. Okay. Now, the points, the data which is given is the concentration of Schottky defect. So, this magnesium oxide will have Schottky defect, which means V mg and VO in the pure form. Okay. And so, V mg is equal to VO, and this how will you calculate? You can calculate this using exponential minus Qs or Hs, delta Hs divided by 2 kT. Okay. So, this for a given value of Qs, we have looked at the values earlier, and this works out to be 1.4 into 10 to the power 11 not 10 per centimeter cube. So, you can refer to previous lectures for the value of Q, and T as you know is 1873 Kelvin, and this can be calculated to be 1.4 into 10 to the power 11. Okay. And so, this is your ionic defect concentration. And now, your electronic defects concentration, this is Ne is equal to NH, and this is given as Nc Nv to the power half into exponential minus of Eg by 2 kT. Okay, that you remember from the previous discussion when we discussed the defects, and you know what is Nc Nv, that can be easily found out. And if you refer to previous lectures, refer to the band gap of magnesium oxide, and this value at this temperature works out to be 3.6 into 10 to the power 9 per centimeter cube. So, I know what is the intrinsic defect concentration, and I know what is the intrinsic electrons and holes concentration. Okay. Now, of course, what we are looking at is we are looking at the calculation of conductivity in both the cases, and we will see what kind of conduction prevails in magnesium oxide. So, now the diffusion coefficient. So, in order to work out the ionic conductivity, you need to know the diffusivity, and diffusion in magnesium oxide takes place by movement of magnesium vacancies, because magnesium ions are smaller than oxygen ions and they tend to be more mobile. So, as a result, we take dVmg into account, and dVmg is given as 0.38 into exponential of minus 2.29 electron volt divided by kT, and this unit is centimeter square per second. So, this is a given value. Okay. Now, you know what is the temperature. So, what is mobility? Now, from the Einstein-Nernst-Einstein relationship, you know that mu v mg, what will this be? This will be now Z E dV mg. So, this will be Z V mg dV mg divided by kT, and I know that for Vmg Z is equal to 2 into 1.6 into 10 to the power minus 19 into dV mg divided by 1.38 10 to the power minus 23 joule per second into 1873 Kelvin, and this will be in Coulomb, and this is in centimeter square per second. So, if you now put in the value of temperature here and you work it out, this comes out to be 3.3 into 10 to the power minus 6 centimeter square per volt second. So, this is the value of ionic mobility mu v mg. From this I can calculate what is sigma Vmg. Sigma Vmg is nothing but Ci. If you go to the previous expressions, let me see on which page we were. Okay, so sigma Vmg was Ci Zi square E square di by kT. Okay, so sigma Ci Zi square E square divided by kT into di. So, this will be Cvmg Zvmg dVmg kT. Okay. Here we made one mistake in the ionic conductivity. I think we need to correct that, and this would be Zi EE, and these two Zi's will cancel each other. So, this will go away. So, this will be Ci. So, you will not have any square here. Okay. So, yes, this is your electrical force. Okay. So, this is Ci Zie di by kT. So, this is one correction that you can make. So, let me just, alright. So, now if I put the values in, what it becomes equal to, Vmg can be calculated as Ci or Cvmg multiplied by Zvmg multiplied by E into mu v mg. Okay. And Cvmg is nothing but your defect concentration. So, this will be, and Zvmg is equal to 2. So, this will be 1.6. Excuse me, let me just, so Cvmg from the previous slide we can take, this is 1.4 into 10 to the power 11. So, I can see this 1.4 into 10 to the power 11 per centimeter cube multiplied by 2 multiplied by 1.6 into 10 to the power minus 19 Coulomb multiplied by 3.3 into 10 to the power minus 6. Okay. Now, if you just calculate these will be, so 1.4 into 2 to the power 2.8, 2.8 into, so this will be approximately 6.6, approximately 10, approximately, okay, 10 multiplied by 10 to the power minus 25 plus 11 10 to the power minus 14, approximately 10 to the power minus 13 ohm centimeter inverse. Okay. So, this is your ionic conductivity. Now, if you look at electronic conductivity, sigma electronic is, so Zi E. So, you can say basically sigma, this is equal to nothing but your N E mu E. So, N E is equal to, from this relation, 3.6 into 9, 3.6 into 10 to the power 9 centimeter cube per centimeter cube into 1.6 10 to the minus 19 coulomb, and we need mu E. Mu E for these materials is approximately equal to 24 centimeter square per volt second. And if you now calculate this, this will be your approximately, this will be 150 approximately. I am just doing the mental maths. So, 150 multiplied by 10 to the power minus 10 ohm centimeter inverse. So, this will be approximately 1.5 into 10 to the power minus 8 ohm centimeter inverse. So, compare these forms. So, here you have sigma electronic of 1.5 10 to the power minus 8 per ohm centimeter, and you have ionic conductivity of 10 to the minus 13 per ohm centimeter. So, clearly in the pure form at this temperature, so at 1500 degree centigrade in pure form, sigma of sigma electronic is much larger than sigma ionic. So, this is the thing in pure form. Now, what happens in the impure form when we dope MgO with some impurity, intentionally or unintentionally, that is a different issue. What happens, that we will see in the next class. Thank you.